In this video, we'll solve the initial value problem y double prime plus 2 times t times y prime minus 4y equals 1 with initial conditions y at 0 equals y prime at 0 equals 0. So the first thing to note is that this t right here is a non-constant coefficient. And so we haven't really dealt with how to solve that. So all our methods in chapter 6, the coefficients of our differential equation were constants. So this shows the power of the Laplace transform. So when we take the Laplace transform on both sides, we start with the Laplace transform of y prime, just as before, and then we add to that plus 2 times, and then I have to take the Laplace transform of t times y prime, and then minus 4 times the Laplace transform of y. And then on the right hand side, I take the Laplace transform of the constant function 1. And what we need to note here is that since t is not a constant, I cannot pull it outside. So because it's not a constant, I cannot use some type of linearity argument to pull that outside my Laplace transform. So we'll have to deal with that in a moment. So the first part is standard. So that is s squared times y of s, and then minus s times y 0 minus y prime of 0. And then we have plus 2 times, and there's a property for the Laplace transform. If you multiply function times t in the t domain, that becomes a derivative in the s domain. So this right here becomes, and you can look it up in the properties for the Laplace transform, negative 1 to the power 1, that comes from the t to the power 1, and then times d ds, so the derivative with respect to s of the Laplace transform of y prime. So we have the Laplace transform of y prime. So the way to get rid of that extra factor of t is by turning that into differentiation in the s domain. And so we subtract 4y of s, and then on the right hand side, the Laplace transform of 1, that's 1 over s. Now, because of our initial conditions being 0, right, that's all 0. This is going to be 0, and this is going to be 0. So what we get then is that the first part is going to be just s squared times y. So here, all the purple stuff just simplifies to s times, or s squared times y of s. And then for the second part, the minus 1 to the power 1 times the positive 2 will actually become negative 2. So I'm going to put in -2 here, and that is multiplied by, and then the derivative of the Laplace transform of y prime. And so that rule tells us that is s times y of s minus y at 0. And then minus 4y of s equals 1 over s. Now again, y at 0, that is 0. And for this derivative, we actually have to use the product rule, right? The derivative of s times y of s. So we still have a little bit of simplification to do for our differential equation. So this is s squared times y of s minus 2 times, and then we have s times the derivative of capital Y with respect to s. Can just write that as y prime here, and then plus 1 times y of s. And then minus 4 times capital Y of s, and that equals 1 over s. Now, if we simplify that, and take the y prime to the front, we get -2 times that s times y prime of s, and then plus and then s squared minus 6 times y of s. So we have the s squared here, then the -2 and the -4 gives us a -6, and that is equal to 1 over s. Now, what we need to notice there is that we have a linear differential equation. And we, in the first chapter, or the second chapter, we learned how to solve these linear differential equations. So what we need to do is we need to write this in standard form. And that means getting rid of the -2s coefficient. So we're going to divide everything by -2s. And so in standard form, our differential equation becomes y prime of s, and then plus 6 minus s squared over 2s squared, no, 2s, right? And we divide by a negative, so I flipped the s squared and the -6 multiplied by -1, and we then multiply that by y of s And on the right hand side, we get minus 1 over 2s squared. So this is a linear differential equation. And what we need to do is we need to figure out what our functions p and q are. The function p is what is in front of y of s, and what's on the right hand side will be our q of s. So here p of s in this linear differential equation is 6 minus s squared over 2s, which can be written down as 3 over s minus 1/2 s. And then we also have q of s. And q of s is equal to negative 1 over 2s squared. And if you recall, to solve that linear differential equation, we then have to find the integrating factor. So the integrating factor mu of t is e to the power and then the antiderivative of s. And so what we get here is that that is e to the power of the antiderivative of 3 over s minus 1/2 s ds. And so that is e to the power antiderivative of 3s, 3 over s, that will turn into an ln. So 3 times ln of s, and then the antiderivative of negative 1/2 s, that gives us negative 1/4 s squared by the power rule. And to simplify this, I'm going to write this as a product, e to the power negative 1 over 4 s squared times e to the power ln of s cubed. So what I did is I brought that 3 inside the ln using properties of logarithms. And so now the e and the ln, they cancel out. So my integrating factor is s cubed e to the power negative s squared over 4. That's my mu of t. So let me summarize that. Mu of t equals s cubed e to the power negative s squared over 4. Then we can solve y for y of s by using the formula y of s equals 1 over mu of s times the antiderivative of mu of s times q of s ds plus c. And I will, in the interest of time, to not make this video too long, I'll leave it up to you to find this antiderivative. It turns out that you can find that antiderivative using substitution. And so the answer that we get is 1 over s cubed e to the power negative s squared over 4 times e to the power negative s squared over 4 plus c. And that can be simplified somewhat to 1 over s cubed, and then these powers of e cancel out, plus c times, and then I can bring that e to the power negative s squared over 4 to the numerator and make the power be positive. So that's e to the power s squared over 4 over s cubed. So that is my y of s. And the big question now is, what is c? So normally we would use the initial conditions to figure out what that constant is, but we already used the initial conditions. Those initial conditions are baked in. So what I'm going to do is I'm going to use the property from the last video, and that states that the limit as s goes to infinity of y of s needs to be equal to 0. And if we look at the limit of y of s, we can clearly see that that is the case for the first term. So if we look at 1 over s cubed and you let s go to infinity, you divide 1 by a really large number that tends to 0. However, for the second part, we have that the top part goes to infinity and the bottom part goes to infinity, right? So if we look at limit as s goes to infinity of e to the power s squared over 4 over s cubed, that is actually infinity over infinity. Both of these go to infinity, and that's an indeterminate form. So what you could do is you could repeatedly use L'Hopital's rule to figure out what that limit is going to be, but we can also argue that e to the power s squared grows much, much faster than s cubed. So the top really is going to win. So we can actually bypass this and say it is infinity. That limit is infinity. But that would contradict this limit unless we let c be equal to 0. So the only way that this can hold, and given this fact, those two things together must imply that c equals 0. And so that means that y of s is actually 1 over s cubed. And then we can find y of t as the inverse Laplace of 1 over s cubed. And that turns out to be t squared over 2. So our solution to the differential equation is t squared over 2.